Good day everyone. So for this video, we're gonna try to solve a problem regarding, of course, still the moment, but this time we will gonna try to solve this using a vector notation form. Okay, so let us recall that um, the same as when we do this problem in a um, scalar notation, but still the principle behind recording the moment is still the same, right? That the moment is just what? The moment is just the summation, or I mean the forces multiplied by the perpendicular distance that acted upon this system about the reference point. Okay, so that is still the concept that we will gonna use. Okay, so first, um, let us read the problem. Okay, so we are tasked here to determine the moment of the 400 Newton force about point O. So as you can see here in our figure, so let us call this figure 1. So this is our given illustration, which shows the different um, data that we need, no? So we have here the 400 Newton force that acted upon at the end of this object about 30 degrees from the clockwise from the positive x-axis, no? And we need to determine the moment that it creates at this point O. So this is our reference point O. Okay, so our technique, if we will gonna solve this problem regarding the vector notation, is that of course we need to use the vector notation forms. Okay, so for our solution, let us first convert the given force, this 400 Newton here, into a vector notation form. So we need to convert the given force into vector notation form. Okay, so how can we convert this 400 Newton at about 30 degrees from the positive x-axis? Okay, so again, let us review. We need to convert this. So from here, we need to determine the I and j component, no? Since this is a 2D. So let me construct a x y axis here. Say this is our x direction, y direction. So therefore, we have here the I, and this is our j component. Okay, and also recall that if we have this kind of of um, of axis, I mean this coordinates x and y, and it is inevitable here for us to show that the moment that this force create is that um, it creates the rotation about the z-axis, right? So at about the k component, or about its k component, about its z-axis, right? So imagine if we have force acted upon at this point, so it creates rotation about this point O. Okay, so again, for the solution, we need first to convert the given force into a vector notation form. Okay, so let us copy this force here. Say say this is our 400 from this point. We have x and y axis, then say this is our 400 Newton, and it is about 30 degrees from this axis, x axis. Okay. Figure 2. This is the FPD of force F. So let me name this 400 Newton as force F. Okay. So from here, in order for us to find the vector form, so we need to find its I and J component, right? It's I and J component. Okay. But since we are given with 400 Newton and then 30 degrees from this positive x-axis, clockwise from this positive x-axis, then we can now easily say that the I component of this 400 Newton is just equal to 400 Newton cosine 30, right? So we have a positive direction. This one, we have positive. Then for the y component, we have the minus 400. What, sine or cosine? Sine. It's now sine 30 degree. Yeah. This is I and this is J, right? Okay. So all in all, our force F in terms of vector notation, so we have 400 cosine 30 is 346.4 I, then minus 400 sine 30 is equal to 200 J. Okay, so since this is a two-dimensional, we only have a I and J component, but we can also write the K component, which is just equal to 0. Okay, just to show or to complete the given vector. Okay, so instead of writing like this, we can write the force F in terms of this vector notation form. Okay, or we can just, let me erase this one, or we can just say, or say that our given force F is equal to how much? 3, 4, let me copy. Yan. Copy. Then let's paste it here. Our force F is equal to this much. Okay. Oops. Okay. So sorry for my drawing. Say this is 5 meters, and from here up to here is 2 meters. Okay. Okay. From here, we already converted our figure, and we use the vector notation form, which is the value of our force is this 1. Okay. after this, since we say that the moment is just the force times the perpendicular distance that acted upon this object, then we also need the representation of the distance. Okay, so we now need to determine the or to find the what we call the position vector. Determine the position vector. Okay, so the position vector is just the vector that is, so let me copy first this figure, since this figure is much better than my drawing. So let me paste it here. Okay, let me erase this part. Okay, so we have our force F, which is equal to this part, 346.4 I minus 200 J, right? So this is our force F. Okay, so what we need is, since we already have our force, then we need our distance, right? So we need to find what we call the position vector, wherein the position vector is just the vector representation from the origin or the point of rotation, wherein from point O up to the position of your force. Okay, so since our force is here, then our position vector is from this origin up to this point. Okay, so just imagine that my drawing is straight now. Okay, so let me call this position vector RA. Okay, so position vector RA is equal to, we also need to determine its I and J component. So its I component is this part, right? So its I component is just 5 meters I, and then the Y component positive, no? Then we have plus 2 meters. 2 meters J, and of course again the K component is just 0. Okay, right? So all in all, we have this force and we have this position. Okay, so now the next thing that we need to do, since we already have the force and position in terms of vector notation form, then we can now get the moment